Hello, this is the prep video for section 5.1, Introduction in Large Sample Confidence Intervals. We're going to kick this off with just a little warm-up that is like a prep problem because this section is really symbols heavy, okay? Like actually everything we do from now on will have lots of symbols, and you'll see mu, sigma, x bar, s, n, and p. And n and p are from the binomial. And what I want you to do is just make a list because you're going to have to know the difference between these. So go make a list and see if you can explain each of these symbols briefly. None of them are the same as each other, okay? So yeah, and like you could find some in like last week's notes or in other parts of the course. Okay, in the last few weeks we've kind of seen all of these, so those are going to be important. So make sure you go label those. Okay, we're going to start with a quick example. Try to like stay with me during this example because I'm going to reference it a lot in class. And the first example is, I just call it the GPA example. It gives you something that you will understand. All right. So here's the estimation or the example that we're going to go through. Sorry, it says we did this before break because these are notes that I used last semester. But what I want you to think is like, let's consider that we take a sample, all right, of 100 students, college students, and we calculate the sample mean GPA. And let's just assume it's like something like 3.045. All right, and that's right. And our goal is to estimate the real mean GPA of a Jones student. So this 3.045, it's called an estimate, right? Sort of like what we did in chapter 3. Okay, so we have this estimate of the GPA. Now, what I want you to realize is this estimate has no chance of being correct. All right, we call that reliability or confidence. I'm not very confident that that's exactly the mean GPA for all Doane students, all right? But it's a really precise estimate, okay? Because it's a single number, so you can kind of like sink your teeth into it. You're like, oh, 3.04, that's lower than I thought, or that's higher than I thought, all right? So these are the ideas we're getting at in this section. On the other hand, we could give an interval estimate, so like something like 3.045 plus or minus 1, okay? We're not talking about how we get the 1 right now, but notice that gives me the interval 2.045 to 4.045, right, when I do the plus and minus. And I think you guys would agree that that's not a very interesting estimate now, right? If I do the plus and minus, you guys probably could have guessed that that's like the real mean GPA is in that range, all right? But it's 100% confident, like it's completely reliable. It's probably true, right? It certainly captures the true mean, but it's not precise because, like I would say, no duh. Everyone knows that the mean GPA will be between a C and an A+ average. All right, so we're looking for a balance of this confidence and precision. So in this first chapter, in section 5.1, we just like kind of try to do this kind of thing, try to balance those two things. Since the population mean will not be exactly equal to the sample mean 3.045, it's best to construct something called a confidence interval around 3.045 that is likely, that has a high probability of covering the population mean. All right, but we don't want it to be a really like an interval that we could guess. We still want it to have some precision, and we'll be able to quantify our level of confidence. It won't be 100%, but maybe it'll be high. Okay, so hopefully you looked up all those symbols because now you're going to start seeing them. So to see how to construct a confidence interval, we let mu, which is the population mean, right? It's an unknown value in a population, and sigma squared is an unknown population variance. And let's say x1 through x1, x2, x3, x100, they're the 100 GPAs. Well, we'll have this sample mean, right? We'll have an observed sample mean, x bar, and it'll be the mean of a large sample. And so the central limit theorem will kick in, and it'll specify that that X bar will come from a normal distribution with mean, mu, and standard deviation equal to sigma over square root of 100. So hopefully you kind of remember those values from this last section, or these last few sections we've done. All right, so according to this summary in your book, I just copied it because it was a lot easier than typing it out. All right, if we have a large sample, right, then this confidence interval will be X bar plus or minus some Z, right, some Z value, looks like a normal distribution value, times sigma of X bar, which is sigma over square root of n. So this, right, so notice that's going to go there. All right, so yeah, we've been doing this kind of thing, right? A mean plus or minus some kind of standard deviation-y thing. And now this carries some kind of confidence level with us. So let's see how we're going to get that Z. The Z is related to that confidence level. Before we do that, I just want to make it clear that I'm going to really expect you to interpret these things well, okay? The book won't always have you do that, but I do. I think it's really important that you understand what you're saying when you're doing something technical. So you're going to say something like, you're going to have a confidence level. I know the symbol's weird, but just think of this as being something like 95%, all right? Some high number, all right? When you're done doing this calculation, you're going to say something like, we are 95% confident that the true population mean, and you'll describe what that is, falls between the lower bound and the upper bound. All right, so you'll do the calculations, the plus and the minus, and you'll get those two bounds. When you write your interpretation, do the entire calculation and write out a sentence that my husband, who is not a statistician, but he's an intelligent person, make sure he would understand it using the contextual language of the problem, all right? That's your job as somebody like an engineer or a statistician or a data analyst, to interpret things for people that don't understand the stuff that you just did. All right, so what about other confidence levels, right? We're not just going to do 95% confidence. Let's first of all, let's figure out how is the 95% Z value calculated. All right, I'm going to draw, I know this is going to be ugly, but normal distribution, that's Z, right? So there's this kind of right, like axis, that's the Z axis, and we have this standard normal distribution, and zeros in the middle. Here's what that value is. If you cut off 95%, all right, so whatever the level is, whatever the value of confidence that you want in the problem, throw it in the middle of the distribution. And then what you're going to do is just find these cutoffs. All right, now don't worry about the symbols. All right, I'm going to write, they're just called alpha over 2s. Don't worry about why is it alpha over 2. If you are worried about it, let me know and I can go through it with you, but don't worry about it. All right, all you're trying to do is find these values. So what you do, throw 95% in the middle, figure out how much goes in each tail. There's 5% left, it's symmetric, 0.025, right? This is 0.025. Doesn't really matter because it's symmetric. You just need to find one of these. So look this up in your table. It's a left hand, right? It's the right type of area for the table. Look up the thing that you get closest to with 0.025, and if you look it up, that negative Z alpha over 2 will be negative 1.96, almost 2, right? Makes sense. Remember the 95% rule, right? 2 standard deviations away, that's just about 2. Now you know where that came from. Real quickly, does a 95% confidence interval actually cover the population mean mu? Well, it depends on whether this particular sample we had happened to be one of those, one whose mean came from the middle 95% of the distribution, or whether it was a sample whose mean was outside, right? So remember, right, there's means that will fall in the middle, and then there's some that are just weirdos, like if you just accidentally, right, got a bunch of people with really high GPAs, right? Like if you just picked all engineering and math majors who have high GPAs, right, then you would probably in that 100 people have a higher GPA than a random sample, like other random samples. Okay, so accidentally you could have a mistake, but there's a 5% chance that this process won't give you something that really captures the true mean. There's no way for sure to know whether you capture the true mean or not. Okay, so let's kind of just finish up this GPA example. So we have that the 95% confidence interval, right, is X bar plus or minus this 1.96, that Z value we could just calculate it, times sigma of X bar. So let's suppose that the sample standard deviation for GPAs is S equals 1. Let's just say we know that it's 1, then the circled quantity is going to be approximately 1.96 times 1 over the square root of 100. So remember, the standard deviation for X bar will end up being sigma over the square root of 100. So our best estimate is the sample standard deviation over square root of 100, okay? Ends up being 0.1. So 95% confidence interval for the mean is 3.045 plus or minus 1.96 times 0.1, all right? And we can use that, do that calculation, and we can estimate the population mean, okay? So we can say, here's our interpretation for my husband. All right, we're 95% confident that the Doane population's mean GPA lies between 2.849 and 3.241. Notice that's much more precise than that like 2.0 to 4.0 value we had, right? And there's a 95% chance that the true mean falls in that range, okay? So that's what a confidence interval is like. And we'll be doing some other values, other calculations with this, and we'll do it in R also. But for now, we're going to do a few by hand. I just want you to kind of get your head around it by hand for a little while, and we'll practice it in class at our next meeting. I just want you to notice that some other specific confidence intervals from you, right? You'd have things like X bar plus or minus S over square root of N would be a 68% interval. This 1.645 is a 95%. So notice, like, as you add confidence, what I want you to see, like, confidence is going up, right? 68%, not very confident. 99.7%, very confident. By the way, in engineering, a lot of times you're in this range, 99%, 99.7%, because it's like a safety issue, right? You're estimating something where somebody's safety is at risk if you don't have your estimate correct. So you want to be confident. But notice that the thing I want you to notice at these errors, which is kind of like our old uncertainty, right? Those errors, look at, they get bigger. So as you're more confident, your errors get bigger. All right, so as confidence increases, right, your precision decreases. Okay, so there's a trade-off in those two things. All right, so I just want you to notice that, right? And really high confidence, these intervals aren't as useful or as interesting. All right, that's all we're going to do. Thanks. I'll see you in class.